In our last episode, I discussed the geochemical makeup of rhodonite, which is a manganese silicate, and is significantly different in chemical composition from the mineral crystal called rhodochrosite, even though they are similar in color, and they both contain manganese. So alright, that being said, let's get hands-on with the geochemistry of rhodochrosite. You've probably seen this mineral before, stunning pink or red crystals, sometimes even banded like a candy cane. But what's really going on inside those colorful layers? Let's start with the basics. Rhodochrosite's chemical formula is MnCO3. That's manganese carbonate. The pink color, that comes straight from the manganese. The more pure the manganese, the more vivid the pink. If iron seeps in or intrudes into the crystal during its formation and replaces some manganese, you'll get a browner, less vibrant color. Chemistry in action, right there. Now, how does rhodochrosite actually form? It needs a very specific recipe. Rhodochrosite occurs in different geological environments such as hydrothermal veins, sedimentary deposits, and metamorphic rocks. First, you need a source of manganese, often from the weathering of rocks that are rich in it, like sedimentary or hydrothermal environments, where it precipitates from manganese-rich fluids in hydrothermal veins related to volcanism. Rhodochrosite is a carbonate mineral where manganese is the primary cation, or in other words, positively charged ion. It can form solid solutions with other carbonate minerals such as calcite and magnesite, resulting in variations in its chemical composition and color. In the metamorphic environment, rhodochrosite is formed through the alteration of manganese-bearing minerals. But manganese on its own isn't enough. You also need carbonate ions, typically dissolved in groundwater. When the two meet under the right pH and temperature, they react and crystallize into rhodochrosite. But here's the cool part. Rhodochrosite doesn't just pop up anywhere. It forms best in low oxygen environments. Why? Because if there's too much oxygen, the manganese likes to oxidize and form other minerals, like pyrolusite, instead. So it's all about the geological environment where the conditions are right, perfect, and remain undisturbed, so that the ionic bonding between manganese ions and carbonate ions occur to form manganese carbonate. Let's zoom in even closer. Every crystal of rhodochrosite is built from tiny repeating units, manganese ions surrounded by 3 carbonate ions. Rhodochrosite occurs as rhombohedral and scalenohedral crystal habit, as well as bladed columnar, stalactic, botryoidal, granular, or massive forms. It can also occur as twinning crystal habit, where the crystals grow together in a symmetrical manner, resembling calcite twinning pattern. Rhodochrosite also occurs in other forms as well, such as crusts, layered structures in veins and cavities. These stack up layer by layer, creating the classic rhombohedral crystal structure. Sometimes, trace elements like calcium, magnesium, or iron will seep or intrude into the crystal and substitute for manganese, altering the mineral's color and crystal shape just a bit. Rhodochrosite has a Mohs hardness of 3.5 to 4, making it a relatively soft mineral, which means it is easily scratched by other substances, including common materials like quartz found in dust. Now, why does this matter? Well, rhodochrosite is more than a pretty face. Geochemists use it to track what was happening in the Earth's geologic past millions of years ago. By analyzing the trace elements and isotopes locked in the crystals, scientists can reconstruct things like ancient temperatures, water chemistry, even how much oxygen was around when the mineral formed. It's like a geochemical timeline. And here's a fun fact. Some of the finest rhodochrosite specimens come from old silver mines in Colorado and Argentina. These environments are perfect for rhodochrosite to grow into big, beautiful crystals, thanks to the process of atomic nucleation and metal-rich and manganese-rich fluids that interact where the chemistry is just right. So next time you see a piece of rhodochrosite, remember, you're looking at the result of a very delicate dance between geochemistry, geologic processes, and time. Not just a pretty mineral, but a record of Earth's history, written in both a pink and red mineral crystal called rhodochrosite. Thanks for joining me on this deep dive into geochemistry. If you want more science breakdowns like this, stay tuned in and remember to subscribe to the Soil Mineralogist channel and click the notification bell.